Everybody on the line here is muted currently. Just myself and Garda are on the mic. If you have any questions as I go along, I'm just looking at the screen. So if you have any questions, please pop them in the chat, and Garda will stop me and call them out for me as we go along. I'm happy to take questions as we go along. We can keep this as informal as we possibly can under the circumstances. And also, we will leave some time at the end, hopefully somewhere in the region of 10 to 15 minutes, where we can open the mics up. We can all have a chat about combustion, answer any questions we might have, look up any follow-ups that need to be done. So for now, I will start talking and carry on with the presentation. And as I say, any questions along the way, please just pop them in the chat and we'll get to them when we can. A little bit of housekeeping. If you didn't hear that on the Zoho webinar thing, you are currently, everybody's muted. Pop things in the chat and we'll deal with it as we go along. We are recording the webinar and we will release it to the participants within 24 hours once we've done this. And should anybody want any additional information beyond the recording itself, please don't hesitate to reach out to myself or Garda. We'll do our best to give you whatever information we have. We like to think of ourselves as an intellectually generous industry, so we're more than happy to share our knowledge and our information with anybody that wants it. To that point, before I get going, a quick shout out of thanks to my friends and colleagues at Novatech, for which I've devised a lot of these slides over the years, having worked for them for many years and worked with them for many years. There's a lot of overlap slides with my friends from there. And a special shout out to Stuart, because they're extremely useful to prove a couple of points. We appreciate you sharing your information and knowledge with us. So I'm Stuart Simmonds. For those of you that haven't met me, I've worked in the industry all my career in a number of different countries and companies, both on the manufacturing side of the business and on the distribution side of the business. We Novatech, for those of you that are a Canadian distributor of analytical instrumentation. We are coast to coast here in Canada, as the little graphic shows in the bottom, and we're located in all the various spots that need to be located in Canada. And we do distribution sales for a number of the world-leading analytical instrumentation companies. We also do, as the pictures described there, sample handling systems, larger shelters and buildings and enclosures. So we have a fairly big engineering team. That's us. We specialize in analyzers only, and we spend a great deal of our time teaching and training and providing information on the industry. Let's jump straight into start right at the very beginning with process analyzers. There are effectively three reasons, and only three reasons, why anybody should buy a process analyzer. And it sort of mirrors the history of the industry itself. Efficiency: how well is my plant doing at doing the job it's supposed to be doing? And can I put an analyzer in place to prove that it's doing it along the way? Am I being safe? Initially, is the plant not going to blow up? Secondary, certainly in the history of our industry, are the people that are working there in a safe environment? And finally, in the last, say, 20 to 30 years, we've started to concern ourselves with what we're pumping out into the environment. Those are the three reasons we buy analyzers, and they sort of mirror the history of the industry as they go along. We were first concerned with efficiency in the plant. Almost every analysis was done in the lab until we started to step out and say, hey, sure, it would be nice to be able to do this measurement on the fly quickly to make sure that my process and my batch was operating correctly, and then I can keep going. And then we say, hey, don't blow my plant up. It's super expensive. Please look after it. Please look after the personnel. How do you put equipment in place to make that happen? And now more recently, hey, it's very important. I'm either being legislated for it, or I'm just concerned because we are now very concerned about things like ESG. Am I doing the right thing? Am I being the best possible consumer of this product and giving away as little as I can in the environmental portion of what we do? Why is that so interesting to combustion control? Well, combustion control done correctly, following the stoichiometry, as we're going to talk about today, actually ticks all three of those boxes all at the same time. It's a win-win-win. If we're efficient, we can prove ourselves safe. If we are efficient and safe, we can actually minimize the risk to the environment at the same time. So in our what does process analyzers do for you portion, we can hit all three boxes all at the same time in combustion control. Which leads into the next question: what is combustion control and what is combustion itself? Well, as it turns out, every one of us, warm-blooded mammals on the planet, is our own little combustion engineer. We are all busy making combustion all day. And it's a very, very simple process. We are all combustion control experts. We are all specializing in the skills of combustion control. We breathe in, we take in fuel, we generate electricity in our bodies, we generate heat to move all those cells around, we expel carbon dioxide and water. The process industry works in a similar way, but obviously on a much more industrial scale. We warm things up, we create reactions, we generate things like steam that's very important to move energy and heat around. We manufacture things like metals and fuel and ceramics. We generate electricity, of course. And finally, possibly more importantly, clinical waste incinerators, for example, at hospitals must operate at exact temperatures to get things done. How do you do all of those things? Well, that's all part of combustion control. That's all part of understanding the efficiency of the control mechanism and making sure that it works well under your circumstances. The important portion here is that we want to minimize the air. What we need to understand under these circumstances is that the process is very dynamic and that it's constantly changing all the time. So we have to understand then that what we're trying to do in the control mechanism of an efficient process is to make sure that we see it and adjust it continually and understand all the parameters that are taking place. There is a fairly complex interplay between what is the chemistry of what's going on and the mechanical design of what we're trying to do. And there's a number of things at play. Next slide, please, Dana.
Can you see it?
No. Yes. All right. From a chemistry perspective, and a chemistry perspective only, I know we have a lot of engineers on the line, but if we look at it from a chemistry perspective, what am I talking about? Well, really these three things, and they're quite commonly termed in the combustion area, the 3 T's. If I provide enough temperature with enough residence time for the things to mix, and then give them turbulence that we make them mix together over that time, then I can leave myself with the best opportunity to make all of that combustion take place. And we understand that, again, as I'd mentioned earlier, in just backyard barbecues. We understand all of these things in terms of how we mix fuel and air with enough heat and enough time and residence to get perfect combustion control. Next slide. So let's talk about the stoichiometry, because we bring that word up a lot in combustion control. What does it really mean? Well, stoichiometry means just really the balance of an equation. Nothing too fancy about that at all. The devil, of course, is in the detail. But the nice thing about combustion control is if we look at it in its simplest form, it is actually a very, very simple application. If we take natural gas, in this case, we're just going to call it methane. But if we take methane, the simplest hydrocarbon, and we combine it under those circumstances with the 3 T's, with oxygen, obviously in our applicable cases, that's going to be air, but we're going to focus on the oxygen for now. And we combust that hydrocarbon, then we generate carbon dioxide, water, and heat. It's hellishly exothermic, depending on what we're burning, and that's what we're interested in here. Under those perfect circumstances, if I can perfectly balance that equation, then it is said to be stoichiometric. And really, that is it. The aim of our game from an efficiency point of view is to be stoichiometric, to make sure that we use the right amount of fuel versus the right amount of oxygen and complete the combustion reaction. If we do that, we get carbon dioxide, water, and we expel heat because it's an exothermic reaction. And next slide, please. Where the industry has never wanted to be, and for very, very good reason, is in this space. I have too much fuel and I have not enough air. The industry itself has evolved that way. So since about the late 1970s and early 1980s, when we changed to the design of combustion control that we regularly use to this day, where they're in situ and we're measuring on the fly as fast as we can, then this was the concept. If I can see lots of air and make sure I have more air than fuel, then I will never get myself into this situation. This is, of course, highly inefficient. We are just not burning enough fuel, but also it's extremely dangerous. And that perhaps is more important to us as individuals. We're leaving behind a lot of uncombusted fuel. If you look at the reaction below, you'll see I take my methane, I have some amount of oxygen in there with nitrogen as air, and I generate some parts of combustion. So I generate some CO2 and some water, but I'm leaving behind some partially combusted fuel. What it doesn't show in here is there are circumstances where if you are that imbalanced, that you'll actually leave uncombusted fuel behind too, which is a major problem. But in a weird twist of fate, the fact that we can generate partially combusted fuel is actually quite useful for us in determining how to fix the problem. So instead of making carbon dioxide, I have enough oxygen to make carbon monoxide. It's still dangerous and it will still burn. But actually, I can use that as a precursor to inefficiency, and I can use that as logic then to get myself out of the hole. Next slide, Carter. Slide. So this is where the industry has found itself for many, many years. How do I make sure that I do the job efficiently and therefore hopefully safe? Well, I just put in tons of air. And historically, that's what has happened. If we put in lots of air and we look for lots of excess oxygen at the back end of the stack, then I can presuppose a number of things. I can presuppose I burnt all my fuel. I don't necessarily know, and we're going to look at that as we go along, but I can presuppose that I burnt most of my fuel. And therefore I can be relatively efficient at the same time. But I can also presuppose if I burnt all my fuel that I'm safe. And that, for most plants, if they didn't have the time to really evaluate and look at control and look at efficiency, was good enough. And there are still vast portions of the industry that work under this mechanism. Hey, I got 7, 8, 9, 10% excess oxygen in my stack. That's okay. I'm safe, the plant's happy, we're relatively efficient, I'm burning all my fuel. Yeah, all of those things are somewhat true, but they are not efficiency control. It's not stoichiometric chemistry. And also, we give rise to some other problems as we go along. Next slide, Carter, please. So when we think about it in terms of measurement, what does that mean to us and how do we resolve that problem? Well, there are a few things to note, and we can spend a lot more time looking at how to maximize efficiency of a process. But if you look at this graph very quickly with me, the yellow going away to the right is excess oxygen. The red going up very steeply vertically to the left is uncombusted fuel, partially combusted fuel. Where I want to be is somewhere as efficiently along the curve between the two as I possibly can. If I measure oxygen only, then I am actually effectively shooting blindly to a certain extent. If I see lots of oxygen, I know I am somewhere in that yellow zone, but I have no idea about whether that's efficient or not. And I'll show you later why that number is entirely arbitrary, whether efficiency at one plant is 2%, but efficiency at another plant is 6%, or what you think is efficient at 2 is actually not efficient, and vice versa. So measuring oxygen only gets you to the control. I've controlled the burn. I burnt it, it's okay. I'm pretty sure I'm safe, although there are some caveats to that. The only other way to really know if I step into the efficiency world is to start looking at the partial products of combustion. And that's where the job gets interesting. So if I start looking for combustibles, the things that are left behind because they didn't quite do the job, then I can find myself a sweet spot for where I can keep my control mechanism and my efficiency curves solid. As you see on my picture there, in theory, that could be all the way to the left-hand side, right on the edge of that shoulder. For anyone that's worked in a plant and seen it go inefficient, you know that that is an extremely rapid rise in carbon monoxide or combustibles. And to be on that shoulder is quite useful. It's very difficult to control in that mechanism. So we tend to find ourselves coming a little further down where the minimum amount of oxygen meets the minimum amount of combustibles, and we try and control in that place. If we do that, then we are maximizing the efficiency, keeping ourselves safe, and we're also minimizing emissions, which we'll talk about in a minute. Next slide, please. A quick aside as we go along, and it's become more and more important as the industry has changed. We talk regularly about combustibles, and it's a useful mechanism for us, and it relates mostly to the way we make the measurement. So it talks about the things that we might not have completely combusted. And in the most common cases with hydrocarbons, we're talking about carbon monoxide, and we're talking about some potential rise of hydrogen. The sensors themselves are non-specific. They are calibrated towards CO, but in reality, anything that will combust at the level on that catalytic sensor, and we can talk about that another day, will be measured. So we don't call it a dedicated CO analyzer, we call it a combustibles analyzer. And it will see other things, particularly and notably hydrogen, should it be there. That has become more useful as the hydrogen conversation becomes part of our combustion fuel process. But it is worth noting. And it is worth noting against newer technologies that are now playing in the combustion zone, such as tunable diode lasers, which are dedicated CO measurements. So they can add some advantage in terms of being discretely a CO analyzer, but they will not measure hydrogen. So there is a problem and a relationship between those two things. We tend to interchange the words regularly, whether we talk about CO, whether we talk about combustibles, we tend to overlap and mix them. But it is important to keep it clear in your mind that there are some analyzers that will only measure CO, and there are some analyzers that will measure the combustibles available, which just happens to be mostly CO under the circumstances that we work with. Next slide, please. So to wrap up the chemistry bit before we move on, what does that mean to us? The most important portion of this is to look at that stuff on the right-hand side, because it mirrors the history of the industry. Most people, and even right in the very beginning, nobody ever wanted to be in the red zone. It's hellishly wasteful of all that fuel. It's also extremely dangerous. And you see there in the numbers that you give up massive amounts of BTU. Of course you do. You're not burning the fuel, so you're not generating the heat. So nobody wants to be in the red zone. Where do they put themselves? Well, unless they have really tight control, and unless they're willing to take the time to look at it and make the additional measurements, then the safest place to be is right down in the bottom in the yellow zone. You look at that number, and it's an interesting one. It doesn't look like a lot of BTUs given up. And in some cases, that's maybe true. But actually, if you get out the Excel spreadsheet and you get the smart guys to do the numbers, then you realize that the difference between the yellow zone and the green zone for a fairly big industrial plant is millions and millions of dollars of fuel. So as we step forward in the industry now, we start to say, wait a minute, how do I get myself from yellow to green? And what does it take? What measurements do I need to put in place? What control mechanisms do I need to put in place? And can I get myself there? The other portion of this I leave because it's a relevant portion of the process analyzer industry. It was designed and made by somebody within the industry, and it captures all of the combustion control mechanism all in one space. I'm going to skip over it quickly today because we've blown a lot of time getting ourselves up and running here. But the bit I do want to note for you, which is quite important, is at the top on the right there in the little yellow stripe is the rise of emissions. And what that says is we now need to be more conscious of the fact that if we leave lots of oxygen behind, like we have always done in the industry, then we give rise to greater emissions. And I'm going to talk about that in a minute, because that is quite important. But the other point to note here is efficiency is always positive oxygen, which is very, very useful. That's a useful accolade for us because now we have a dynamic scale to work with. It's never zero. So we can work with that idea and build it into the logic of what we do. Next slide, please, go. We have to bear in mind the two sides of this argument as we step forward. The one side is inefficient oxygen, not enough air. And the dangers of not enough air are extremely real. If we don't have enough air and we don't understand what we're doing, we can create all kinds of problems. Firstly, we're inefficient, which is, to the money folks, a big deal. Secondly, we're extremely dangerous, which is a big deal to the plant and a big deal to the human that's standing right next to it. We can also create maintenance problems from inside the process. So we haven't quite blown the place up. It hasn't quite got that bad, but we are making a mess on the inside of this process. We are coking things up because it's not burning very well. We are getting impingement flames, which I'm going to show you in a minute, are a big problem, where all the combustion should be taking place in the combustion zone, but actually because we're not doing a very good job down here, it's actually taking place in other areas. And it's flashing up in other areas. These are where the potential dangers come in from explosions. But under small circumstances, they are just flames creeping up into areas they shouldn't be, causing undue stress into tubing and other portions of the plant. And of course, it's just a loss of fuel. So we don't want to be here. It doesn't make sense to be here. And of course, it's extremely dangerous to be here. And that tends to lead people to being overly zealously careful. But if we take control of the plant and we understand the chemistry behind it, then we don't actually need to flip to the other side of this equation. We can find ourselves in the happy middle. Got that one slide? Flipping to the other side of that equation is this, and I like to bring it up as we go along. Emissions generally, certainly historically, have related to the stuff that's bound in the fuel. If you're burning coal, if you're burning crappy oil, then it has bound products in it, molecules in it, that will react with oxygen and will generate our emissions, notably NOx and SOx. So if we're burning anything that related to the sulfur plant that has some H2S in it, that's where we get our SO2. We have to deal with those things these days, of course we do, and we have minimum and maximum requirements for those, daily limits, et cetera, et cetera, et cetera. That's little we can do about that in the combustion control mechanism. The same thing for NOx. If you have bound nitrogen in your coal, for example, you're going to generate NOx as you emit it, as you combust. But if we leave a lot of very, very hot oxygen, it is this crazy, wonderful molecule that will react with anything it can get its hands on. It loves to react. And if we leave lots of it behind in the stack at a nice hot temperature, all swirling around with all those other gases, particularly, strangely enough, the most benign gas of all, nitrogen, then we can thermally generate NOx. So even under the best of circumstances, burning the best fuel, if we go overly zealously cautious and add lots of oxygen in, we can actually make our emissions worse, even though we think we're doing the right thing. And it's an important point to note as we drive down emission measurements, as we get closer and closer and tighter with our legislation. Where's my nitrogen? Where's my NOx coming from? Well, I'm just making it because I'm not doing my job properly in the combustion control zone. Got it? So what is my right level of oxygen? Well, the answer, of course, is it depends. And it depends on a couple of factors, and we're going to talk about them as we go along here. The first and most important point to note is it's the fuel. How efficient can I make my fuel burn? How hot it is different from how efficient it is. So there is an argument for burning coal because it burns long and slow and hot, but it's, as you see here, requires a lot less, is a lot more inefficient and a lot harder to control that mechanism than it would be to say natural gas at the lower end. Some people are surprised by these numbers, but genuinely, particularly in Alberta, where we're doing a lot of work with natural gas fired burners, there are a lot of companies now that are genuinely getting down to 1% or less than 1% excess oxygen in the stack as they take control of their process. It's very important. The other point to note, which I mentioned very briefly in a previous slide, is the oxygen number is always positive, which is super, super helpful. It's not zero. The most efficient point isn't to see no oxygen, it's to always see some oxygen. And that really helps when we're trying to control something. Because when we put our mechanism in place and have an analyzer there making the measurement, it is always there. That number should always exist. It should always be positive. What that number should be is a conversation that we will have next, because there are many, many factors that can interfere with what that true number is. And the answer is, we can build all the charts we like to say, hey, if you're burning natural gas, you can get down to 1% or less than 1% excess air. But what we really need to do is say, hey, let's take a look at your plant and see how you operate it, see how old it is, see what you do in it, see what the shape of it is, and then we decide what the excess oxygen number is. So the real answer is, what is the excess oxygen number level should be? Well, it depends on which plant we're working in. And that's where we step away from the theory and step out into the real world and have a look at what's going on. Got it? From a chemistry point of view, which is slightly annoying to engineers because we make everything look super, super simple, when in reality, there's lots more complexity going on out there. For us, it comes down to a few things that we need to think about, and then we need to address all the many other mechanical things all wrapped up inside of it. Firstly, what does it look like? What are we trying to do? What does a burner look like? How do we mix the fuel and the air together? Then secondly, how do we control that fit? How do we control introduction. How fast is it whistling through the process? How does it mix and turbulent? How much time does it have together? How do we mix it all together? How do we control that? Is it being controlled by some external mechanism, boiler management control system, advanced burner control, something clever like that? And then finally, and sort of less important from a measurement point of view, but certainly very important from the plant's point of view, the heat management. Once you generate all this stuff, what do you do with it? Where does it go? How fast does it whistle through? How much residence time does it do to warm up the thing it was trying to warm up or burn the thing it was trying to burn? So there's a number of things in there that factor into how the plant is designed and how the combustion control is used that has an impact on how we try and make it efficient. What you need to do then is to step back and look at an individual plant, to spend time with a combustion engineer, to walk a plant down and say, hey, look, here's all the theory. I can tell you exactly what stoichiometry means and how we can get there. And it's important to know that stuff. It's a great foundation for sure. But then you need to look at that plant. You need to stand in front of it and say, okay, well, where are we going to do this? How are we going to do it? What does it mean if I do this? And those are the next few slides I want to get through. Hopefully we have enough time, having burnt a bunch at the beginning here. Apologies. So next slide, please, go. I've tried to break it down into a couple of spaces. And there is a lot of complexity in here. And I've wonderfully spent some time with some great combustion engineers. And it's a really tricky task to understand how to maximize an individual plant. But from my perspective, there are two discrete sections to think about. One is mechanically what it does. What does it look like? How big is it? How old is it? What are we trying to do here? How much load do you give it? If you're a turn down plant in Ontario, waiting to be peaked up and down, then it's very hard to be efficient if you're only idling at 15%, 20%. So those things are quite important. Or are you trying to run this boiler as hard as you can? Those things make a big difference. And generally speaking, most combustion engineers will tell you, it's much better to be efficient if you're 80% or above load. If you're running a big vessel at a very low load, it's very hard to be efficient at all. So there are complexities in there. The other portion of this conversation is about the control of the measurement itself. What are you going to do with it when I give it to you? How are we going to operate and manipulate those measurements? Are they going to be in a loop? Are they going to be part of a bigger control mechanism, an advanced burner control system? Are you involved in a safety shutdown system? And those things become important, partly in which analyzers you decide you want to pick, but also in how efficient they are, how well they work, how much uptime they have. There's a number of other things that go in place there. And generally speaking then, if we want to be more efficient, we need to start adding a few of those additional components. Next slide, Garda, please. There are a few things affecting the combustion control mechanism. Fuel quality, of course, we talked a little bit about that. Airflow and how it comes in. So the quality of the air and the speed at which it comes in and how we control the mechanism of that speed is very important. The design mechanism inside, what does it look like? They are all shaped differently. All burners and boilers are all different, and they all have different feelings about them, and whether they were good designs or bad designs, or whether they were designed for a certain type of fuel and now we need a different type of fuel and it doesn't work quite as well. So there's lots of factors that factor into that portion of it. And then the environmental conditions. It makes a big difference whether you're trying to burn in the peak of summer in Winnipeg or the peak of winter in Winnipeg. There's quite a lot of environmental condition that takes place. So from a combustion control engineer's point of view, then they have to factor all of these things in, and they have to build margin in to be able to understand that and how they build efficiency and stoichiometry under those circumstances. Got it? Thank you. Okay, point one. What is it doing? So if we were to come to the plant and say, hey, help me be efficient. Okay, well, what is this process? Is it a process heater? Am I an incinerator? What am I trying to do here? What's the point of the combustion? And how big is it? How many burner tips do you have? How many vessels do you have? Do you have various combustion zones? Does it all move into one space? Is it new? Is it old? You know, if we were under new conditions, it's wonderful. We can all, if we get the opportunity to sit with the engineers and say, hey, put me a measurement here, here, and here, and here. That's the perfect spot. If you're going to run this thing at 80% or more, then everything's going to be great. We'll get you to the most efficient you could possibly be. Or you turn up at a plant and say, hey, it's 55 years old and we're doing the best we can. Let's see what we can achieve. The two very, very different arguments. the number of points of measurement, the design of the technology. Are we going across the whole process? Are we doing point measurements? Are we doing a combination of the two? There's a whole bunch of things that get involved in there. Carla? This is a quick example of one type of heater. It's a common one. A draft heater is one of the most common ways to generate heat. And I bring it up because it brings up a major problem. Problem number one. It's a draft heater, which means that just like any chimney, it is sucking its way up and out the bottom, out the top. So sucking from the bottom and drawing its way up and out the top using the heat. And we control that flow with a number of things that inside mechanically. But generally speaking, it is under negative, slightly vacuum pressure on the inside. That means then that as my plant gets old, then the likelihood is that I can suck in air from the outside. And this is a major problem for our industry. It's commonly called tramp air. It's air coming in that doesn't belong in the combustion process and certainly doesn't belong in the understanding of the stoichiometry, but it's an extremely common problem. And it relates for us to a couple of things from a measurement perspective. Historically, we have put a lot of analyzers towards the back end of the plant. We're measuring oxygen only. We bought a fairly simple device. It doesn't like the high temperatures down the bottom, so we put it in the stack. We still regularly call them stack analyzers. A lot of the more modern analyzers are semi-extractive, can take much higher heat. They are cross-stack lasers. They can take much higher heat. They could be much further down in the process and avoid problems of tramp air. The further you go up, the more likelihood you're going to see that air getting sucked in through old valve systems, old flanges, viewing ports if it's old enough. There's a number of spaces it can happen. What does that mean from a measurement point of view? What that means is my oxygen analyzer up here reads plenty of oxygen. It's telling you I've got loss. There's plenty of oxygen here for combustion. But in reality, we're just sucking in air from the outside and making that measurement. If I'm not measuring a combustibles measurement at the same time, then I can get myself in all sorts of problems out of the way. It's not complete. There are all sorts of inefficiencies down below. I am still potentially putting the plant in danger, but I think I'm doing great. So the stoichiometry is not there. It is not an efficient burn. If I were to measure the combustibles measurement at the same place and potentially even a methane measurement at the same place, then I can cover off to say, wait, I'm seeing 4 or 5% oxygen, but actually I'm also seeing the rise of combustibles. Something is amiss. And I have a couple of slides very kindly donated to me from Suncor that show you that problem in real time. We've talked about it. Yeah, thanks, Carter. We've talked about it for many years about these problems, and it's taken me a long time to actually see it in actuality. And our good friend Stan Danoff at Suncor kindly lent me these photos because he'd done it for his own plant. What you're seeing here is secondary burn, impingement, as he likes to call it, as it's commonly called in the industry. And what this means is I am flashing off in those areas that we're marking combustion again. If I were efficient in the radiant combustion zone and were burning all of my fuel perfectly under stoichiometric condition, I wouldn't see this happening. But what is happening here is there are outlets for partially combusted fuel to combust again as it goes further up the process. It shouldn't be combusting here. It's a very, very heavy load on those tubes on the inside. It is potentially dangerous, potentially can crack them. That's where you get tube leaks. We can get flashing, bigger flashing that can cause these pockets of explosion in these areas. Next slide, please, Carter. As you see in this picture, a couple more from Stan. These two ports here are old doors, and he's taken thermal images of them to show you that it's super cold here because I'm sucking in air. I am sucking in air through these leaky ports higher up in the stack, and now I give rise to all of these other problems. And again, you see here in this picture, I'm getting secondary burn. I'm getting impingement burn because my combustion control efficiency is not there in the bottom, even though my analyzers might think they are. If I only have oxygen only, a long way up the stack past these measurements, then I'm seeing loads of oxygen. And I'm telling my control guys, look, it's good. There's lots of oxygen here, nothing to worry about. But actually down in the zone where we should be making measurement, where we should be looking at the combustibles at the same time, we would realize that things are not as happy as we think they are. Next slide. The next point is to look at the actual layout of the plant itself. how do I find the perfect place to put my measurement? If we were building from scratch, as we said, which is, let's be honest, 5% of the time now, 10% of the time, then we could say, hey, this kind of technology, these kind of measurements, you should put them here. This is the perfect place to put them. You'll get the best reading, we'll avoid later problems down the line, everything will be great, we'll get responses as fast as we can. Now we can start tweaking stoichiometry, we can get very, very close. But the reality is we're usually dealing with an existing plant and an existing design. So in that design, where do I want to put my measurements? Do I have the luxury of asking for new nozzles? Can I ask you to put new nozzles on? Yes or no? Or am I going to live with the ones that you have because that's currently where it's at? Maybe those nozzles are great. Maybe they're perfect. Maybe they're not, but you need to look at that. What does it look like on the inside of it? Are there tubes running up and down? Does the flow look nice inside? Am I hitting the laminar flow, or am I just catching some leg on the side that's really not representative of the process? If I want to use a laser and shoot across it, can I see across it? Can I get from one side to the other? Can I get two nozzles to line up? So there's a number of mechanical, physical constraints around what we're doing. The last one is also interesting. Do you do anything inside the process? Anything inside the process that might upset what we're trying to do? Does it mess around with it? Do I need to pull my analyzer out when you do some kind of flood or some kind of clean, shotgun walnut shells in a clinker oven, something like that? There's all sorts of weird little things that happen, and they're worth knowing about. But to my bottom point here, if we're dealing with an existing plant and we know that it has ingress, then we need to think about where best we can put it, or how best we understand the ingress, so that when we're trying to be efficient and stoichiometric, that we can back that ingress out, which is a lot harder to do. Next slide. Here's a great example, and I've left it up there. It'll go into the presentation later, and I will send these slides to everybody. But these are two real conundrums that I've lived through in recent times. The one on the left-hand side is showing you where they would ideally like to put the analyzer. Under these circumstances, none of these are particularly ideal. None of these work particularly well for me, but we would have to see if we can make them work. That's the practical and the reality of the situation. Is that good enough? Because that's really all I got. And the ones on the left-hand side is an existing plant. That is the floor of a furnace, and the measurements exist currently bolted up into the floor. Not where you want to be, but sometimes that's where you have to be. It made sense to that plant that they were there. That was the best possible place. It was transitioning between one portion of a furnace and another portion. There was no way to get on top of it, but you could walk underneath the furnace and put them underneath the bottom. Is it a useful spot to do? Can we put them there and still make the measurement maintainable and reliable and give us good enough chemistry to start looking at the efficiencies and the stoichiometry? The answer is partially yes, but those are the realities that we have to live with. Next slide, Gunnar. One more slide from my friend Stan. This one is fantastic. So this one is a smoke stack test where they're positively pushing smoke through a vessel and seeing if there are any leaks. And as you see, there are a lot of leaks. So where's my oxygen analyzer right now? Well, it's above this. If it's above this, then when the process is running and it's under slightly negative pressure, then of course I'm going to be sucking in air. What does that mean? That means that's a reality for us. How do we make sense of that from a stoichiometry point of view to see if we can make this plant as efficient as we can? There's a number of things we can do. We can either potentially move the measurement to a better spot. That would be ideal. If we can't, then we add in the combustion, we add in the methane, we build as much of a picture as we possibly can. We're seeing high oxygen, but it doesn't necessarily relate to the bottom. We have to do a number of chemistry tests if we can in that process with the engineers to say, okay, let's play around with the oxygen number and see if we can relate that to efficiency in the bottom, and then know that 7% oxygen at the top here is actually 2% oxygen at the bottom or something like that. But there are mechanisms to do that. And if you want to achieve perfect stoichiometry, then that's what you have to do. The physical conditions of the gas are important. What measurements we want to make are important. And as we step towards efficiency, then of course what we're saying is don't go oxygen only. It really only gives you a control. It doesn't give you efficiency. You have to measure the CO or the combustibles in there. And there's a third measurement that we look at now, which relates to safety. I can throw in a methane measurement, which says if you're burning natural gas and a whole pocket of it misses the combustion zone, then I can tell you it's there. So wonderful safety mechanism, and it's more of an add-in to the process, something for another day. There are two other points to note here. Perhaps you need something more advanced than just the local CSA requirements, for example, in Canada, that you might want to step in and have some sort of boiler code, some sort of pressure directive. There are a couple of other mechanisms that come at play when you think about analyzers. Next slide. The final point, and I mentioned it at the beginning, what are you going to do with my measurement when I give it to you? Because that's quite important. Are you just taking signals into the control room to let the control operators have a feeling for what's going on? Am I part of a boiler management system? That's usually yes to most of those questions. Am I part of an advanced management system where I am on the trim valve? It is a point of note for process analyzers that very rarely are we in the control mechanism of a plant. We are usually information providers to other people to let them control the plant. In the case of combustion, we are occasionally afforded the luxury or the respect of the analyzer being put on a trim valve where we can actually operate, open and close the amount of air that comes in. That adds an extra heightened respect for the analyzer, but also pressure for the analyzer. It has to be good. It has to be reliable. It can't give me false readings. This is very, very important stuff. So is it going to be part of that? And then another step further than that, is it going to be part of a safety integrated system? Are you then going to be part of a system that decides to shut a plant down if it doesn't like it, where it takes control of the operation and says, nope, too dangerous now, everybody hands off. We are now instituting a system that will safely put this plant back down. And the analyzer often plays a portion of that. If it does play a portion role in that, then of course it now has to be super reliable, and you have to guarantee that its ability to do the job is very important.
We have a question.
Yes,
I think it's related to a previous slide, asking, is there a maximum distance for the laser type O2 analyzer? And I assume they mean optical path length.
Like path length?
Yeah.
In theory, no. In theory, no. But you still have to shine the light from one side to the other, and you have to align it. So it's more of a practical limitation than it is about the laser lamp itself. So one of the nice things about lasers is, you can think of it almost like a laser light pen, but it can shine a significant distance, and it has a lot of signal to noise ratio. So it can go quite a long way. And because of the technology itself, you can lose quite a lot of that transmission along the way and still make a healthy measurement. So those things are all positive. So in that case, then you can go quite a significant number of meters. Where the problem lies is, can I keep it aligned, i.e. are the walls flexing, and can I brace it enough so that I can shine from one side of the flange to the other side of the flange and still hit the target? Sometimes that's a practical limitation. And sometimes if you're burning something other than natural gas and you've got some opacity in there, then does it start to be too opaque, too dusty, too dirty for me to get through it? But more commonly, certainly from a Canadian perspective, where we burn a lot of gas-related fuels these days, then it is more about, can I keep it aligned? That's usually the distance. And then what's going on the inside. So I practically want to put it here, but there's some tubing and some valving or a turn or something, those kind of things. Couple of notes, and I know we're running late. Apologies with the mess up at the beginning. This is all too common still in our industry. Explosions and fires are all too common, and they relate to a number of factors. And they relate normally to some sort of hiccup or mistake. It's not normally a full mistake going on all the time. It is often a hiccup. There is occasionally this leakage into an idling furnace. That's a problem. But a lot of them relate to an event happening and coming and going. Certainly a loss of a flame and a pocket of gas getting past it. Things shooting through too fast where the valve control is lost. An accumulation in one area or a pocket of gas. And sadly, those things happen more often than not. So all part of the argument about stoichiometry and perfect measurement and adding those additional measurements is to try and mitigate this loss, of course. We're trying to find a way to say, hey, we can take control of combustion. There's no reason why we can't take control of the combustion zone and understand what's going on quick enough to avoid ourselves getting into this situation. So my last slide, one more slide, last slide. Relates to the SIS on the previous slide relates exactly to that, which is to say, you can now have analyzers that have determined how good they are to be put into a safety integrated shutdown system. So there is a mechanism within inside that says, I can provide for you information that allows this analyzer to be part of a system that will automatically control and shut down the process and help you get where you want to be. So let's recap, and I apologize for running late, and I will try and open if anyone that wants to stay on a little bit, I'll stay on for questions. Apologies for the hiccups at the beginning, but just to recap, combustion control is relatively simple. We do it every minute of the day. Well, it turns out how much you eat, but certainly you're breathing in and out on a regular basis, and you're combining that with the fuel in your body to create heat. We are our own little combustion engineers. The reasons for incomplete combustion can be many. They can be part of the mechanism of how we do it. It can be part of the mechanics of the way the plant is designed. But we can noodle out most of those problems. We can certainly get to the point where we understand them. And one of the reasons is we are lucky, if you like, that there is a halfway house between complete combustion and completely incomplete combustion, where we have this partial combustion. And it's a very useful tool from the hydrocarbon bucket, strangely enough, that we never meant for it to happen, but it works very well in our favor. I can start looking at very, very small levels of partially combusted fuel, CO, and potentially hydrogen, to start to interrupt the problem and get rid of it quickly. And that has become part of this efficiency conversation. If it wasn't there, if we burn pure hydrogen, for example, we lose that window. So as we step forward into our future and think about 100% hydrogen burning combustion processes, if you like, there isn't a halfway house. You either burn hydrogen or you don't. You either see water or you see hydrogen. So how do we run that mechanism? Well, we'll have to come up with that plan in the future should it get there. But as it stands, we have this ability to say, oh, yeah, it's working, but it's not really working very well. We need to adjust. And that actually becomes very, very useful to us. You measure oxygen, you know you're in control. You add in combustibles, and now we can be efficient. You look at methane to just say, hey, I think I'm safe, but I'm proven I'm safe. I'm seeing no uncombusted fuel. And that's really the essence of understanding the stoichiometry of the science of combustion control. I put one last slide up here just as a point of note, which is to say, we didn't talk about technology today. We strictly talked about the science. But of course, there is a lot of play in there, and one of those questions relates to lasers versus point measurements. So perhaps it's something for another day. Perhaps it's something for an ironed out webinar that doesn't have any errors in it, to talk about how the technologies are used, how the measurements are devised, and why you would pick one over another, why you might want a combination of both. The industry has evolved somewhat in the last 20 years, and there's lots to talk about on that side. And perhaps one day we'll come back, regather, and talk about a second webinar that relates directly to where those technologies get used in the framework of all of that theory that we talked about today. Thanks, everyone. I went over time. I'm super apologetic for the mess of us trying to set up this system. I'm not sure what's going on with my computer, but if anyone's got any questions, we'll open it up quickly. Anyone wants to stay on, I'll happily sit here for a little bit and answer any questions anybody has.
Thank you, Stu. Actually, we have a few questions. The first one is, what are the set point low or high alarm set point for CH4, O2, and CO combustible?
So it depends a little bit on the plant itself. But if you were say, let's take a natural gas burner, for example, you can, if we can avoid all the other spurious trampy air things that are going on, and we just look at the combustion zone, then you can start looking at oxygen controlled at 1%, which means to the plant then that they would likely alarm at something 3,000 or 4,000 degrees less than that. So the ppm less, so say 0.5% or 0.6 or 0.7% oxygen, they start to say, wait a minute, I think we need to control here. And likewise above it, if they are in good control of their boiler management system, they might have a band that says 0.7 to 1.3. This is where I want the oxygen to be when the load is like this. So when the combustion engine says we're running healthy and stable, everything's all coming in quite under control, that's good. From the CO perspective, then we would say you should see almost no CO burning methane. So we would expect a floor measurement, nominally call it 20 ppm. It could well be 0, but it's quite useful to have a positive number as opposed to 0. People like a dynamic number. So most analyzers will say something like 20, and then as it starts to rise, you need to decide what you want to do about it. And most plants have a shut-in safety number. So there might be hundreds of ppm before they say, hey, we don't like this, this is starting to look dangerous. But they might have a primary, a first point alarm say, at 100, tell me, because I'm getting inefficient, something's not right. I shouldn't see this. From a methane perspective, it should be 0, and it should always be 0. It's a safety analyzer reading, and really what it's saying there is, look, I hope I never see anything for you. I shouldn't. If everything works in the combustion zone, I should always see 0. They usually range quite wide, 0 to 5% usually, because what they're looking for is a leak. And when a leak happens, you want to actually see quite a lot of the leak, not a tiny little window of the leak. So what it says is, hey, I'll just tell you the moment I show up. And that's really what happens. You would alarm very quickly if you saw any methane. You would set it very low. 0.5%, let's say.
Thank you, Stu. Another question, it's a bit long. You consider CO and H2 as criteria for incomplete combustion for the case of positive O2. What about unburned hydrocarbons like CH4, C2H6, C3H8, etc.?
Yeah. Again, it's a good question, and it is a real possibility. If we lose control of the combustion zone, then you can potentially see quite a lot of uncombusted fuel. Can you see completely uncombusted? That's the question, and that's why you might want a methane sensor. It's methane, but it's calibrated. It's calibrated to methane, but actually it would respond to any hydrocarbon that comes through it. It's a very simple device. It's just it's basic burning, but but the idea behind that is if we follow the physical parameters of the process. So if you spent time talking to a combustion engineer and said, hey, look, I'm looking at the temperature. So I've got your analyzer, that's great. And I'm trying to help it. I'm trying to let it help me be efficient. But I'm also looking at thermocouple temperatures, pressures, flows. I'm pretty sure burner tips, all of these things all have their own pieces of instrumentation that help them, or to a greater or lesser extent, most places have one. And when you have that in place, then you can infer that you're up and running and everything's healthy. The most dangerous point for a plant is to start up and shut down, as they're trying to light it all off and get it all up to temperature, to auto ignition temperatures, and the same thing coming down. We're trying to bring it back down. We're going to do maintenance. It's been 3 years, 4 years, and we want to now make these safety checks, do all these other things. So at that stage, you could potentially see uncombusted hydrocarbon. And under those circumstances, that's where that safety measurement comes in. But you would hope under normal circumstances that you would never see it. If we run good control, then the chances of a full pocket of gas getting past, that's where you get those nasty pictures of explosions, for sure.
One more question. Can having too much oxygen, excess air, result in unsafe combustion control?
Yes. Yes. So when we talk about the chemistry of it, we're looking at it under the ideal condition. And I flashed it up quickly today, but the 3 T's are really what we chemists think about. Do I have enough temperature? Do I have enough time? And do I have enough turbulence to combine the fuel with the air? And if those things are great, then I should have enough residency time to create combustion. If I do that, then I'm good. That doesn't say that I'm efficient. It just says that I've given it all the opportunity it can to burn with itself. If I whistled through a massive amount of air, I can make the place very unsafe. I can blow the flames out. I can shoot huge pockets of gas past it and not allow it residency time. There's a number of things I can do. So in theory, lots of oxygen is where the industry has always wanted to be because it feels safe. But you have to factor in exactly how it got itself to all the way up into the stack and whether it was safe as it went through. The answer is not necessarily. So there are circumstances where, you can have a lot of oxygen and still be unsafe. The other example of that, of course, is this thing about tramp air. I can look at the stack and say, hey, I've got 6-7% oxygen here. I must be burning everything. But as my good friend Stan has showed me, that doesn't mean that down here below in the combustion zone where I'm supposed to be doing the job, that I have enough air. And maybe I don't. Maybe my plant is so old and leaky that actually I'm just sucking in huge amounts of oxygen further up. And my analyzer is telling me that it thinks it's okay, but actually it's not. How do I fix that problem? If I had a combustible sensor in that analyzer at the same time, it would give me that weird reading. Wait a minute, 8% oxygen, but I'm starting to see combustibles. Something is not right. Something is not right. So you have to look at that. The other thing that would come into play would be the mechanics of it. So where we would take measurements where they're pretty sure they're getting impingement flashes. So as I get to my analyzer, maybe it has all combusted, but it's combusting in the wrong zones. And you would pick that up with thermocouples and other pieces of instrumentation that tell you it's not healthy. So you have to combine, as my slides were trying to allude to, you have to combine what the reality of the plant is with the logic of what efficiency means and how you get there.
One more question. For projects that have added new CO analyzers, what was the lowest excess O2 they were previously operating at? Currently, our plant operates around 3 to 5% without CO analyzers.
Which is good, which is probably potentially very good. And that's, so there is a return on investment, and I'll see if I can find it. There is a way to calculate based on size, load, fuel, about efficiency. And what does it mean if I went from 1% oxygen to 2% oxygen and 3% and so on? And there is a way of doing that. And it is a bit of a generic way of looking at it. As you saw from my slide there, it feels like you give up a small amount of efficiency between lots of excess air and being as minimum as you can. But in reality, over time, with a lot of fuel, if the plant is reasonably sized, that can actually add up to significant amounts of dollars. So there is a way of looking at that. If you were to do it on a plant itself, and I have been witness to this a couple of times in my career, that the plant itself can do that test. So, and you have to do it under a controlled mechanism, but what you can do then is they can set up a system where they actually adjust the amount of air coming in and look at the efficiency and look at all the physical property of what's going on inside the plant under a controlled structure to say, okay, this is where we think the most efficient point is. This looks to be slightly inefficient now. This looks to be unnecessarily excess. When we control the plant and then we imagine that the combustion taking place inside the combustion zone, which is not a steady state, it's a little series of explosions, it's flames. Where can I put my control of the analyzer readings to make sure that I'm never bouncing too much or too little? And there's the band. That's what they look for. So the answer is you can probably noodle it out. We can probably give you a rough idea. But really, the best way to do it is to actually do the test, to do a combustion test.
The last question, great presentation. Is the CIL certification for all three sensors and signals? An example, oxygen, CO, and methane, 4 to 20 MA or dry contacts? So normally, almost every analyzer will still give you hard wire. So everyone gets 4 to 20s and dry contacts. Almost every analyzer manufacturer will do it that way. But of course, more modern analyzers will give you Ethernet, Modbus, all sorts of other clever things. If you step into that SIL argument, then that's where that additional information is useful and also necessary, because that's how they're proven. Most of them are proving themselves that way. So they're saying, hey, yeah, look, I'm a 99.5% uptime analyzer because I'm looking at all of these diagnostics inside myself to check that I'm healthy, that I'm happy, that I'm not degrading, that I have the mechanism internally to predict my errors, because you need me to be available 99.9% of the time, whatever SIL2 is or whatever rating you get yourself to. So there is a complexity to that, and there are diagnostic routines within analyzers that are checking that for themselves, so self-diagnostically. And it's useful then to take that signal back and have it look at it for you. So you pull it into a computer in the control room or on an analyzer tech desk or wherever you need it to be. And you can bring that data in, you can store it, particularly should you ever need to call it back up because something happened, or you need to talk about maintenance, or you need to complain because the analyzer went down, whatever it is. So there's usually most modern analyzers have a lot of diagnostic routine inside them to do that. In terms of which ones are actually SIL, there is a bit of a question there, and it relates a little bit to the technology. The technology of oxygen measurement is extremely ironed out. Whether it's a zirconia dioxide technology or a laser diode technology, they are very well proven and very well founded, and they have a long history. And so therefore getting SIL rated versions of those analyzers is easier to do.
When it comes to combustibles measurement, it's a little bit more tricky because of the type of measurement it is, but it's not impossible to get. And certainly most analyzer manufacturers are working towards that in terms of SIL rating. On the methane side, it's a safety measurement, and normally it's not normally required to be SIL itself, because it's not normally meant to do anything for you. But it is supposed to be there to say, hey, I see it. Okay, stop. I'm seeing uncombusted fuel now. But there is a lot in that. And that is a fairly evolving industry, of course, as most of these plants get more and more safety related, and the control mechanisms get better. So the boiler management systems, the advanced boiler control systems, safety shutdown systems are all, that industry is growing, and our industry is running behind it to catch up.
Another question, how often to verify the analyzer and how often to calibrate?
Often do we calibrate an analyzer? Generally speaking, not as often as people think they need to be calibrated, I think is probably the answer to it. There are a lot of plants, so the industry in the whole, process analyzer industry as a whole, is trending towards not wanting to calibrate as often as it used to, because it's being driven by the end users to do it that way. They have less people, less time, they want more reliability, they want more inbuilt diagnostics to say, I don't need to keep being calibrated. And certainly historically, if you ask a bunch of old service techs, they'll tell you part of the problem with analyzers is they get calibrated too often, because the calibration not done correctly introduces error, and there's a number of other things that take place. So I think that there are related problems that come with that, where the industry is saying, calibrate me less and just check my diagnostics. I'm watching myself all the time. That said, there are a lot of plants that have a standard requirement internally to say, hey, I want to know that you're a critical measurement, and I want to know that you are checked out regularly. So if you look at manuals, lasers will tell you they don't need to be done but once a year, but most people will want to do it more regularly than that. And for conventional zirconia type analyzers, it's usually people do it once a month, but it could be pushed out. Certainly with more modern analyzers with a lot of diagnostic routine, there's no reason why it needs to be done that regularly. And again, depends a little bit on the measurements themselves. Oxygen is a rock solid technology. It's absolutely ironed out. From a combustion perspective, zirconia has been in the industry 55 years, maybe a little bit more now, and is completely ironed out. We'd like to argue that we sell the best one on the planet, but in reality, there's a lot of very good zirconia sensors out there. The analyzer package is different, but the sensors themselves are pretty good. For the rest of it, ppm, a combustible sensor is a relatively simple device, asked to do a fairly low measurement these days. We've tweaked combustion down. We're asking for analyzers to be more and more sensitive, to be more controlled at the lower end. And in reality, that technology is, at the bottom end of its limit. So it can be a little noisier. And some people have a problem with that. But in reality, we have to remember two things. Firstly, we have to remember that there's a dynamism to what's going on in the measurement. So they will not be rock solid. They shouldn't be rock solid. It would be a mistake to look at an analyzer and see the oxygen and the combustibles readings not move because of the way the process is working. So we want them to be dynamic in some way. And because we're only measuring, say if we're burning methane and we're measuring, what should be almost no CO, no combustible, then noise is highlighted. You've got a handful of ppms, and if it bounces up 10 or 15 ppms, it looks like a very, very noisy signal. But in reality, what's going on in that great big vessel where you're just looking at a handful of ppms is nothing. So you have to build logic in to the control mechanism to say, don't worry about it going from 20 to 60, worry about when it goes over 100 or 150. And that industry has got better too. It used to be pretty noisy. There used to be a reasonable amount of drift in it. And the analyzers have got better at managing themselves to be a little bit more stable on the combustible side. But anyone that's been here, that's worked in combustion for a long time, will know it's always been a little bit of a troublesome measurement because of the way, you're trying to control this very, very low ppm oxygen combustible measurement. I hope that answered the question.
Thank you, Stu. The last comment that we have is that oxygen and combustibles are SIL 2.
Right. Yes. That's what we need. That's what most analyzer requirements are. And And that's what you would want if you're going to put it into an SIS system. That's where the industry needs to get you. So if that, you know, maybe that's the first point of, you know, if the plant is ready to be at that stage with a SIS system requiring still analyzers, then that's the first point of conversation. What analyzers can provide this? And then what do we do with those analyzers to make sure that they operate safely within the safety zone, but are also providing me with efficiency? Because really those two things can be a separate conversation. This one's going to help me shut down the plant if it doesn't like what it sees. This one is also trying to make sure that I'm efficiently burning my process. They kind of come together and mean the same thing in the end. But when you're looking at devising them and where you're putting them and what you're planning to do with them, they can start out as separate conversations.
Thank you, Stu. No
Thank
further
you.
questions.
We are well over time, and I really apologize for whatever was going on with my PC and the setup. But we appreciate everyone hanging in there and staying with us. Greatly appreciate it. Hopefully it was useful. If God and I will send out some information, send out, you know, what was left of the webinar. If anybody wants anything, please feel free to let us know. We're more than happy to share what we know and what we have. And we are sort of starting to think that we might do a second webinar that would relate to technology. And we've talked about what stoichiometry means. We've talked about what it means in the plant and how you practically apply it. Now let's look at what analyzers go where and what they do. And maybe there's a conversation there. We can delve into that. If there's interest in that, I think Gada will send out a survey.
Okay.
If there's
Yes,
interest
correct.
in that, then please let us know, and we're very happy to put that one on without any of the technical hitches. Okay, thank you, everyone. Appreciate
Thank
the
you.
time.
Thank you, everyone.